the shortest path. So how do we know if all our vertices are connected with the shortest path possible? Let's have a look at a network. So this is going to be a little bit big. We've got A, B, C, D, E, F, G, and H. And let's draw some edges in. Oops. Should be the vertices. Let's put the vertices back in. T, G. It's connected to here. Let's add some weightings to the vertices. 5, 10, 5, 7, 2, 6, 8, 3, and 1. Now, what is the shortest path from A to H? So, I guess we can have a look. So, we've got the path A, B, E to H. We've got the path A, C, F to H, and A, D, G to H. Which one of those is the shortest? So we can work that out by going 5 plus 7, so this is the top path, plus 8. This is the middle path, 10 plus 2 plus 3. And we've got the bottom path, 5 plus 6 plus 1. This one gives us 20. This one gives us 15. And this one gives us 12. And we can see that the bottom path is the shortest path, but it wasn't very practical because we had to look at every path and add them all up and go from there. But it's not always practical to look at every single path and find the shortest path. So we're going to learn a way to do it without having to do that. And there's another algorithm for this. I'm not even going to attempt to pronounce this one, but that is how you spell it. Okay, and this is very similar to Prim's algorithm, but we're considering the vertex we start with every time. So let's draw in a network. A, B, C, D, and E. Going to draw some edges in. Let's add some weightings. So 4, 4, 2, 3, 6, and 5. And we want to know what's the shortest path from A to E. And we're going to use this algorithm to help us do that. So again, we're going to start with all the vertices just on their own. A, B, C, D, and E. And we have to pick a starting vertex. We're going to pick A, but you can, well, we want to go from A to E, so yeah, it'd be good to start with A. And we want to connect any vertex as long as it has any vertex to A with the minimum distance possible. So our options to go from A is to go from A to B or from A to D. And the one with minimum distance is the one from A to B, which is 5. So we're going to do that. Connect that one, which is 5. Now, with this algorithm, we need to always go back to our starting vertex to work out the minimum distance, to add another vertex in. So my options are, I can go from A to D, I can go from A to B to C, I can go from A to B to E. So I'm looking at adding in another vertex, but always starting from A. And they're my only options to add in another vertex. So from A to D would give me a weighting of 6. From A to B to C, that'd be A to B is 5, then B to C is 4. So that'd be 5 plus 4 gives me 9. And A to B to E, A to B is 5 and B to E is 4, so that's also 9. So out of all those, the minimum one is A to D, which gives us 6, so that's the one we're going to draw in. And again, we need add another vertex to the tree we've just formed by always considering the path from A. So now my options is going from A to B to C. I can go from A to B to E. I can go from A to D to E, or I could go from A to D to C. So A to B to C is going to give us 9. A to B to E is also going to give us 9. A to D to E is going to give us 8. And A to D to C is also going to give us 9. So out of all those, the minimum one is the 8, so A to D to E, so that's my next edge I need to draw in of 2. And finally, we just need to add in C. So my options are A to B to C, or A to D to C. So if we go, we've already worked out A to B to C is 9, and A to D to C is also 9, so it actually doesn't matter which edge we draw in out of those. I might just draw this edge in here, so 3. And now we've created a way to get the shortest path from A to E. So the shortest path now from A to E is obvious because we go from A to D to E, and we get a weighting of 9. So that's our shortest possible path we can take now. So now from A to D to E is going to give us our shortest path from there, which is, sorry, I said 9, it's actually 6 plus 2, which is 8. So that's our shortest path from A to E.